There we go.
No, that's what we can do. All right, you don't have to watch this, you can watch me. You can watch the live me. All right, so the way we're going to link mechanical type motion, okay, that's a little strange, is we're going to make pretend track that goes across the board, a little cart. Is it better in black, guys?
Hi, Sarah.
Can you see it better?
Yeah, it's better in black.
Okay, all right. Come in, join us, Sarah. All right, then we're going to hang a spring. How was Upton, Sarah?
Good.
Was it fun?
Yeah, the kids don't talk there, but
Oh,
good.
okay. And then I'm going to tie my marker, all right, to this. Got it? Okay. And I'm going to make the spring bounce up and down. Okay? So we're going to put the spring into simple harmonic motion. While the spring bounces up and down, like this, I'm going to push the cart. So if we put those two motion pieces together, predict for me what the picture is going to look like that I make on the board. Agreed. And if I can be nice and consistent with my speed, yeah, that was okay. Can you kind of see it on the projector?
Yeah.
Okay. Yeah, I know. And then it'll do it half a second later. All right. This is a sine wave. We are going to use it as a physical representation for electromagnetic waves, sound waves, basically to everything that we're going to study for wave motion. We're going to start with the anatomy, but it is created by a regular, repeating, simple harmonic motion. The dashed line is the equilibrium position. Okay? If this were a water wave, like a wave in Lake Michigan, this would be the level of the water when there's no wind. Make sense? So it's zero displacement. Something you need to know about waves is that they are created or they're made out of energy. The wave itself is made out of energy. It can, like any form of energy, move particles, objects, etc. Sometimes that movement is converted into heat. Sometimes, in this case, it's converted into waves. But it's like an optical illusion to think that the wave actually travels across the board. Or the water travels across the board. If it did, if the water traveled from the middle of Lake Michigan onto, we'd have a donut, wouldn't we? Right? All the water around the edges and nothing in the middle. So it's the energy that's moving across the board, and it gives like an optical illusion. Doesn't it look like the waves are moving up onto shore? You just get a little bit of water movement. In fact, the water actually, if you were to like tag a water molecule, what you would see is this. So a water molecule would actually just sort of move in a circle, and anybody who's ever, thrown a tennis ball out into Lake Michigan knows that the tennis ball pretty much just stays out there. Eventually, due to something called longshore transport, it would eventually end up on the beach, but in general, it just kind of bobs up and down, right? So let's now talk about some different parts. Any place where the wave crosses this equilibrium position, that spot is called a node. These are all nodes. Zero displacement. I'm going to demonstrate these in a really, really cool way in a little bit. The height of the wave, height from the equilibrium position to the maximum displacement, That height is called amplitude. It's the same here. Okay, so the amplitude is equal top or bottom. Technically, the amplitude can be measured anywhere. So at a node, give me the number value for the amplitude. 0. And let's say that this is like a water wave, so these are 2-foot waves, right? If it's a 2-foot wave, is the amplitude 2 feet or 1 feet?
1 foot.
That's correct. The Coast Guard, basically anybody who's measuring waves, measures them from bottom to top. So a 2-foot wave would have an amplitude of 1 foot. Very good. These are called transverse waves. We also will talk about longitudinal waves. For a transverse wave, the definition is the direction of travel of the wave energy is perpendicular to the displacement. So what that means is that if the shore is the far side of the board, right, it'll look like the waves are traveling from right to left. So the energy is actually traveling toward the shore. The displacement is always in the direction of the amplitude. So it's a transverse wave when those two are perpendicular. Transverse electromagnetic waves actually have 3 axes around which they move, or around which the energy moves. There's a component that travels like up and down, in like what we consider the Y direction. There's a component that travels back and forth, which we would consider in the X direction. And then the Z is actually like the axis that sort of links the two. So every electromagnetic wave has an electric component, a magnetic component, ergo the name electromagnetic. They're actually pretty dang complicated, and we use them every day. The theory of electromagnetism is how you charge your cell phone. So in transverse waves like this, when there's sort of a top and a bottom, and of course in space there's no up and down, right? A top and a bottom, it gets a special like anatomical term. The top is called the crest, and you may have studied this like in middle school. What's the bottom called?
Trough.
Yep, it's actually pronounced, I've heard it pronounced 2 ways. Trough, like where pigs eat, yes. Or trow, if you want to sound like, you know, yeah, like a superior, snooty, whatever, science nerd. I don't care what you call it, but I have heard it pronounced trow as well as trough. Up and down, by the way, is arbitrary. Have I talked to you about the Peters map? Okay, we'll pause that because it's not absolutely critical, but it is an extra credit opportunity. So for those of you viewing this from home, hello, Peters map for extra credit. And then we'll look it up. Has anybody ever heard of the Peters map?